Good afternoon, everyone. Thank you so much for joining us here today. My name is Anna, and I'm a product manager working on AR Core. In this session, we'll be talking about our Faces and Images features, walking through some use case ideas, and then showing you how you can get started. AR is all about blending the physical world with the virtual. Last year, we launched AR Core 1.0, aiming to help you build apps that can understand the environment and place objects and information in it. But to truly blend the physical and the virtual, your phone needs to be able to augment people, places, and things in a realistic way. What we're covering here today is the set of capabilities AR Core provides so you can get started doing just that. Let's dive right in with Faces. I'll walk us through why we built Augmented Faces and what exactly it is. And then Ranjith, a tech lead on the team, will show you how you can get started with our APIs. So imagine that you come up with a brilliant idea for a feature, and this feature involves rendering assets on top of faces. Building out the algorithms in order to do this from scratch is pretty difficult, so you look around for some options. You want to make sure that your feature works at scale on a lot of different types of phones. You try out a couple of the options, you're not sure if they work quite the way you need them to, and you also find that many cost money to use. That's why we built Augmented Faces into AR Core. Augmented Faces allows you to have face capabilities in your own app, works at scale, and is available at no charge. And with the improvements we're announcing here at I/O, it'll work on over 1 billion devices. So what exactly is Augmented Faces? Augmented Faces is an API that provides you with 3 things. First, a center pose for a face, which marks the middle of a head and is useful when you want to do things like render a hat. Second, region poses, which are useful when you want to render assets on a nose or around the ears. And last but not least, a 468-point dense 3D face mesh that allows you to paint detailed textures that accurately follow a face. We do all of this, even the 3D face mesh, without specialized hardware by using machine learning. This enables Augmented Faces to work at scale, which was a key requirement we heard from you, our developers. We're really excited about this, especially because face-based AR unlocks a wide array of use cases, ranging from beauty and accessory try-ons to fun face effects that your users can enjoy with their friends. A great example of a developer that's already started using Augmented Faces is Meitu. They're known for their widely popular photo editing apps that offer advanced beauty effects. They've used our 3D face mesh to create even more innovative effects and to speed up their development process. The 2 face effects that you see here will be available next week on Android in their Beauty Plus app. If you're physically here with us at I/O, another place that you can try out Augmented Faces is at our sandbox. We've built out this fun photo booth experience that you see here. And what you see is that we're able to trace facial features in detail because of the quality of our face mesh. Today, we're also excited to announce that we're bringing that same face mesh to iOS. Since the mesh data structure is the same across both platforms, you'll be able to create one asset that runs across both iOS and Android. Just like our Android solution, Augmented Faces on iOS does not require a depth sensor, so it will work on all ARKit devices. Combined with our AR Core certified devices, Augmented Faces will run on a total of over 1 billion devices. Ranjith will be joining me now so we can show you how this looks on an iPhone 6s, which is nearly a 4-year-old device. So this is an effect that Meitu has built for their Beauty Plus app using our mesh on iOS. So what you're seeing right now is that as Ranjith turns his head, the 3D party hat asset is following his head very well. And now when Ranjith opens his mouth, what we get is a fun little birthday surprise. This is just one example of the delightful experiences that you can create with AR. Our iOS APIs will be available later this summer, and we can't wait to see what you build. Now, I'll hand it over to Ranjith, who will be diving more into the technical details.
Thank you, Anna. Hello, everyone. I'm Ranjith Kagati. I'm a tech lead in AR Core, mainly focusing on augmented faces part of the SDK. In this section, I'll explain you what are the building blocks required to create an Android app with face effects. I'll also give you a sneak peek under the hood, so what goes on in AR Core to enable this feature for our developers. I'll also walk you through some code snippets of a sample application that implements this face effects. We'll mainly discuss about two face effects. One on the left, there is a couple of fox ears and a nose attached somewhat rigidly to the face. So when the head moves, turns, rotates, you see that the virtual content moves along with it. On the right side, there is a face paint overlaid on top of the face. And this not only moves when the head moves, but it also stretches and expands as the person opens the mouth, makes some facial expressions and gestures. What are all the building blocks required? We need virtual content. We need real images with human faces. And we need metadata about the face, as in where the face is looking at, how is it oriented, and what are the attachment points on the face where we can attach this virtual content. We also need a way to blend all these together into a composite image that you can show it to the user. But don't worry, you don't have to build all these blocks yourself. We will provide SDKs to make it easier for you to develop such an app. As an app developer, you'll be mostly responsible on creating the experiences to create the virtual content. In AR Core, we create and we configure and control camera to provide good quality images for this use case. AR Core also processes these images to output metadata information. In this case, region pose, one on the nose and two on the either sides of the forehead. And also we provide a center pose, the 6 DOF information in the form of pose. We also provide you a SceneForm SDK. This makes it straightforward to render realistic 3D scenes in both AR and non-AR cases without having to go through the complexities of low-level OpenGL API. This is one rendering approach to render these effects. You could as well use Unity or Unreal engines if you are interested to so. Augmented Faces supports both Unity and Unreal on Android. Similarly, if you are interested in developing a face mask or a face tattoo, we provide you a dense 3D face mesh onto which you can overlay the texture information. The face mesh is designed in such a way that more vertices are assigned to the parts of the face which are feature-rich, like lips, eyes, edges of the nose, and vertices are sparsely distributed on less feature-rich areas like foreheads and chin. So each of the vertex will provide a X, Y, Z, the coordinates, and also give you a U and V texture coordinate for associating a texture. We also give you a 3-axis normals that you could use it to apply any lighting effects on the face or even to smooth out the face effect. In summary, AR Core provides region poses and face mesh app developer creates the virtual content, and we have SceneForm, Unity, and Unreal to combine all these into a composite image. How does it all work? How is ARCore able to provide a 3D face mesh from a 2D image without any depth hardware? We use machine learning models that are built on top of TensorFlow Lite platform to achieve this. And the processing pipeline is optimized to run on device in real time. We use a technique called transfer learning, wherein we train the neural network for two objectives. One, to predict 3D vertices, and to predict 2D contours. To predict 3D vertices, we train it with synthetic 3D dataset and use this neural network as a starting point for the next stage of training. In this next stage, we use annotated dataset, annotated real-world dataset to to train the model for 2D contour prediction. The resulting network not only predicts 3D vertices from a synthetic dataset, but can also perform well from 2D images. We want to make sure this solution works for everyone. So we train the network with geographically diverse data sets so that it works for all types of faces, wider faces, taller faces, and all types of skin colors. So we have 3D face mesh, but why do we really need 3D face mesh? Take a look at this picture of my colleague, Luis. What's special about this image is Luis does not wear glasses. So what you see there is virtual glasses, and see how accurately it tracks the face. Even the sides of the glasses frame tracks the head movement very well. It looks so realistic, I had to cycle through different colors to convey that it is indeed virtual glass and not real. Now let me freeze the video when the face is at an extreme angle. Notice how a part of the virtual glasses is behind the nose. To achieve this, you need to have 3D information about the face, that there is space between nose and the cheek where you can actually render the virtual image. So this is what ARCore provides. And to enable these complex algorithms on mobile devices, we have multiple adaptive algorithms built into ARCore. These algorithms sense dynamically how much time it has taken to process previous images and adjust accordingly various parameters of the pipeline. We use multiple ML models, one optimized for higher quality, and one optimized for higher performance when the compute resources are really challenging. We also adjust pipeline parameters such as inference rates so that we slow down, we skip few images and instead replace that with interpolation data. With all these techniques, what you get is a full frame rate experience for your user. So we provide face mesh and region poses at full camera frame rate while handling all these techniques internal to ARCore. With this background, we are now ready to build the app in 3 steps. Step 1, create virtual content. Step 2, configure ARCore. Step 3, configure SceneForm or other rendering engines to build your app. To create virtual content, we provide a canonical face mesh in an FBX file format in our SDK. So you download the FBX file, import it into a 3D software, and create your own virtual content. Or you could even reuse your existing content and attach it to the canonical face mesh. So this is the step that decides which parts of the face should control what virtual asset. Similarly, to build 2D texture content, we provide a template texture. We listen to you, developers. Recently, when we launched augmented faces, developers expressed interest that they want to know which vertices corresponds to what parts of the face. So in our latest SDKs, we are going to include this template texture, which is a flattened version of the face mesh. And various regions of the face is demarked with these guided lines. You import this template texture as a layer in your image editing software and apply your own face paint effect as another layer on top of it. You can adjust where that tattoo or a face paint should appear. And export it as a PNG file by hiding the template texture and only exporting the content you created. Now that we have virtual content, it's time to write code and associate that, use that virtual content. First, we will configure ARCore. ARCore by default is configured to run plane finding on rear-facing cameras. We will override that configuration using this step to configure it for front camera and to output 3D face mesh. This is the step. This is an indication to ARCore that it should run the model inferences to generate face mesh every frame. Now let's move to the step 3. In your main app activity, in onCreate method, import the virtual content you created. This is a scene form construct to load 3D content into scene form. I'm making an assumption here that you already imported this into Android Studio, and the resource is available in resources folder. Similarly, you can import the 2D texture you designed into scene form using the texture builder. Now let's create a listener that listens to the updates from ARCore every frame. As I mentioned, augmented faces provides information about vertices. Vertices include texture coordinates, XYZ components, and normals, as well as region poses. But you don't have to work with all these components yourself. This is where the new additions to scene form comes from, where it supports natively augmented face node. So you create an augmented face node of scene form using ARCore's augmented faces API. Now, the number of lines of coding you have to do is very few. On such a face node, you set 3D asset and a 2D texture. And that's it. With 3 simple steps, ta-da, you have an Android app with face effects. So everything we discussed now is already available on Android on our developer page. You can download the SDK and build your apps. This was about augmented faces. Now I will hand it over to Ashish to talk about augmented images.
Thank you, Ranjit. Thank you, Ranjit. Good afternoon, everyone. I'm glad so many of you could join us today. My name is Ashish. I'm a product manager at Google, and I work on ARCore. I'll be specifically talking about augmented images. For the next 15 to 20 minutes, we're going to go through 4 topics. The first one is the rationale behind augmented images. Why did we design augmented images? What's it good for? Number 2, we're going to talk about how augmented images works. And we're going to specifically talk about this in the context of 2 apps that we are showcasing here at I/O. Number 3, we're going to talk about a few updates that we are doing, few significant updates that we are doing to ARCore as part of the ARCore launch, to augmented images as part of the ARCore launch. And lastly, we want to talk about how do you, as developers, take all of this and put augmented images into your own app. So let's start. Why augmented images in the first place? So today, people frequently interact with physical images. Whether they are at a store, they're looking at some product, reading the product signage to understand more about the product. Or they could be at a movie theater, and they could be looking at a movie poster to learn more about the movie. Or they could be at a venue like Google I/O, where it's actually large and they're kind of lost, and they're looking at a map, a physical map, to figure out where they are. Our goal with augmented images is to take these interactions that people have with physical images and make them a lot more engaging and make them a lot more useful to the users in context. We're showcasing one such example here at the sandbox right across this corner. Here, users who would be able to scan product signage, in this case, of an espresso machine. And as soon as they scan the product signage, you would see 3D overlays of product features right on top of the object. This is a super powerful way for manufacturers of these appliances to convey their product benefits, to convey their product features in a way that they could otherwise not do with just plain 2D text or 2D signage. And as Anna had mentioned earlier, the most powerful AR experiences are the ones that are able to take the real and take the physical and blend them together realistically. This is an example where you're able to take virtual content and blend it on top of a real-world object in the right context. So how does augmented images work? Let's take a look. At a high level, augmented images does three things. The first one is it's able to recognize a pre-registered image. So in this case of the espresso machine demo that we just talked about, the app developer has registered the signage as an augmented image inside the app. Second, when the users scan the augmented image, augmented images will give you a 6 degrees of freedom pose of the image with respect to the image. What does that mean? So for example, if this was the image, and this is the device, once I'm done scanning my image, what it tells me is the position of my device with respect to the image in X, in Y, and in Z. It also tells me the orientation with respect to the image in pitch, yaw, and roll. So with these 6 numbers, the X, Y, Z, and the pitch, yaw, roll, you're able to describe the position and orientation of the device or the image accurately. And this is what allows you to go to the third step, which is to take this information and augment 3D content on top of it. And when you augment 3D content on top of the image or offset with the image, the content would stay there regardless of how you move around your device. And that creates this illusion of the virtual content being stuck to the real world. So as you might have heard from Sundar during the keynote, we've launched this experience called Explore I/O as part of the I/O 2019 app. This allows the attendees to go and scan physical signage that you might have seen around. And as soon as you scan physical signage, you are able to see what's around the signage in terms of landmarks. So where is the nearest sandbox for demos, or where are the code labs? You should be able to just pan your camera on your phone and be able to see that. Let's deconstruct this experience to figure out how augmented images is being leveraged in here to power this experience. The first thing we have is that we have 50 such unique signposts, which are placed at very, very precise locations all across the Google I/O venue. And you have these landmarks. Just because we have designed the venue, we know where exactly each of these landmarks are with respect to the signposts. For example, I know that there's a signpost right outside, and the session stage number 6 is right here. So the signposts and the landmarks maintain a common frame of reference. Now, when a user goes ahead and scans a signpost, what augmented images does, it provides the 6 degrees of freedom pose of the device with respect to the augmented image. So now you combine the position of the device with respect to the image and the information about the landmarks with respect to the image. And what you have is the information about where the landmarks are with respect to the device. This is what allows you to overlay content right on top of the physical world. And as you move your device around, you're able to see this content stay in place. We are also excited to announce several significant updates to augmented images as part of the AR Core release this I/O. And a lot of this has been in response to feedback that we've heard from you developers. We've had a couple of algorithmic improvements under the hood, which lead to much higher tracking precision and much higher detection recall. What does that mean for developers? So when you start anchoring virtual content on top of real physical objects, that's when your margin of error in terms of how much can the content shift around while you're tracking, the margin of error there is actually super small. And so the improvements that we made in the past several quarters will allow you to now start annotating real-world physical objects and give your users an illusion that it's actually there. We also now allow you to track multiple images in the scene, not just one image, but multiple images in the scene. And lastly, this part I'm most excited about is the ability to track images that are not static, but can move around, and we continue to track them. Let's look at that for a bit. In previous ARCore versions, ARCore used to give you back a pose of the image at 2 hertz, so roughly every 2 times a second. And that means that if the image was to move around while the session is going on, it is possible that the virtual content would lag because the images are not being tracked continuously. So what we've done is now the image poses are being given at 30 hertz. So we've increased the frequency at which we give you updates by 15x. But at the same time, we've made sure that the power consumption does not rise. So the overall power consumption rises by less than 3% for a 15x increase in the frequency of the poses that we provide. And we also realize that as your images move around, they might go out of your camera field of view. And with the higher detection recall, we are able to help with that as well. And we are excited with what some of our early developers are doing with moving augmented images. JD.com is an e-commerce company, and they've come up with an app called JD AR Books. This is an educational app for really young children that teaches them how to spell simple English words. So as you scan a letter C, you would see an augmentation come up on top of letter C. And as you move C, the augmentation moves along with it. And it's only when you place all the 3 letters together that an achievement is unlocked, and you actually see a virtual car in this case. If you were to misplace the letters, you would actually not see that happening. As you've seen in most of these examples so far, what we've done in ARCore is take the real world and add more information on top of it. But ARCore can also do more things in terms of be able to make you visualize the world in a different way. Not just add new stuff, but be able to visualize it in a different way. So if you know, US currency traditionally does not feature faces of women. Most of the faces on US currency is today of prominent men. A former US treasurer, Rosie Rios, has partnered with the Google Creative Lab. And they've created this AR experience called Notable Women. This allows users to take US currency and be able to replace the faces on US currency with the faces of women who've made a tremendous impact on US. And this helps people learn more about these remarkable women. Hopefully, all of these examples have sparked some ideas in terms of what all you can do with augmented images. Now we'll spend the next few minutes talking about how do you actually take augmented images and put it as part of your own app. There are 3 steps at a high level to create an augmented images app. The first one is to create a database of images that will be used to trigger the experience. Number 2 is to create and configure an ARCore session to use augmented images. And finally, at runtime, you query the camera at every frame at 30 hertz and figure out what is the pose of the image that you're tracking and render content on top of it. Let's go through each of these steps. Here, in the first step, you'll identify all the set of images that you would want to trigger experiences of. Today, we allow you to create a database of up to 1,000 images, 1,000 unique images that your users can scan and trigger your experience. We provide you an offline tool that you can use to generate this database. We also provide you a way to do this at runtime in your app as well. For the purpose of this, the code snippets that are going to follow, we're going to assume that an augmented images database has already been created offline. The second thing with any AR Core app is to create and configure an AR Core session to do a particular thing. As Ranjit did so in the case of augmented faces, we'll do so now in the case of augmented images. You create an AR Core session, and then you take this augmented image database that you had created earlier, you decode it, and you pass along the decoded database as a parameter into AR Core config session. With these simple code lines, you should be able to create and configure an AR Core session. Then you move along to, at runtime, what you do is you start querying the pose of all the images that you're tracking at every camera frame. And what AR Code would return back is the pose of each of the images and the tracking status of each of these images. Whether or not it's tracking or not tracking, the image might have gone out of view. So it will give you a status update. And as long as the images are tracking, you can go ahead and render physical content right on top of these images. So in these three simple steps, you should be able to create a basic augmented images app. But we'd like you to go a bit further. There are certain things that we have learned from experimenting with this, and we call them our best practices. As you know, the augmented images database lives and dies by the quality of the images that you'll be tracking or scanning. It is very important that you choose images that are great for your experience. And we provide you a tool that will tell you if your image is good or bad in terms of a score for an augmented images experience. So what are the images that qualify as good images and will give you a great score? The first one is that images that avoid heavy compression. We don't want heavily pixelated images. You also want to choose images that have at least a 300 by 300 resolution. And lastly, you want to choose images which have distinct, non-repetitive features. The last point is a bit subtle, and it's lost a lot of times. So we've got a couple of examples in here. Here you see, on the left-hand side, you see this image of a globe. If you see this globe, there are lots of distinct high-contrast patterns on this image. And there's nothing that repeats across the image. So it's a really good image to track and to recognize as an augmented image. But the image on the right-hand side, the one of the building, it has lots of features. But once you actually start scanning the image, you understand that there are these lots of repeating windows that go across the image. And so it is very easy for the algorithms under the hood to get confused as to what they're looking at. And so such an image would not be ideally suited for an augmented images experience. And our tool will tell you that the score of this image is super low. So we would highly encourage that you choose images that are closer to the ones that give you a score of 100. Also, another important step is how do you onboard users? AR is a very, very new interactive experience for most people. And it is important that you teach users how to be successful in the experience. The first step in an augmented images experience is for the user to scan an image. So how do you tell a user that, hey, you are supposed to scan an image to start the experience? A couple of visual cues will help. In our case, we tend to use these brackets, these visual brackets that show up in your camera field of view. And these steer the users towards scanning the image. Simple text can also help. We've seen that if you do either of these things, we've seen a remarkable uptake in the success ratio in terms of how users perceive your app. You also want to make sure that the users are not just scanning tiny images. They get closer if the images are small. So make sure you size the brackets appropriately so users are putting in the images at least 25% of the screen space. With these code lines and best practices, you should be able to create a really good augmented images app. And we'd love to know what you'd be up to with this. And we are here to help. As part of I/O, we have several code labs. Augmented Faces has its own code lab. So does Augmented Images. In less than 30 to 45 minutes, you should be able to create your first augmented image or augmented face app. There's also a sandbox demo if you're looking for inspiration on what could AR do. There's a sandbox which is right across the street here. And our dev site, developers.google.com/AR, has the latest and the most up-to-date information on our APIs and on our SDK. And as for us, myself, Ranjit, and Anna, we'll stick around after the presentation is done. If you folks have any questions on the code that we presented, if you have questions on use cases, or if you're looking for more features and have questions on that, we'd love to hear from you. So please stop by. We'll hang around right here. Thank you again all for joining us. We really appreciate it, and hope you all have a productive I/O.